Okay, all right. So technical problem solving, as far as the flavor of the event, is to gather data, then to process the data, and then from this data, give an answer. So if you look at the new standards, you're kind of going along with science and engineering practices, where a question is asked, and then you have to come up with some type of plan on how to go about gathering that data to answer that question. So it's different from an AP type question where you would have content knowledge already and you're answering the question based on things that you've already learned. By the time I get done with this, I will give you a couple practice labs to give you a help on how to use the equipment and what kind of questions or what kind of data you can gather. And I'm anticipating that that's the type of data that you would need to answer the question that ultimately is going to be asked. So, and again, because we're limited to a 50-minute block, the extent of how open inquiry this can be is limited because they don't have an infinite amount of time. So the nature of the beast says I got to control this a little bit more than I like to. I also try to set up duplicate stations so that the kids don't rotate. They come in, and for that 50 minutes, they have all the equipment they need to answer 2 or 3 questions, depending on what the event supervisor decides to use. But they do it without having to go from one station to another, which ends their ability to work on one question because they're no longer at that equipment. Now, from an event supervisor standpoint, that means that you've got to think about how many kids are you going to have in the room at one time, because you're going to need, let's say you do 10 teams at a time, you're going to have 10 sets of equipment, and you're going to have a room set up so that you can have 10 stations. And typically a flat top table, kind of like in a physics lab, works really well. Most things I do seem to involve water, so a sink in that room is a great asset. I try to design my events to run from a grocery store list, so I've tried to keep away from dangerous chemicals or things that would be hard to come up with, but normal safety precautions, you know, you still have to put in place. But I try to make it so that we don't have to worry about waste or safety issues or having stuff that we can't come up with. So we're going to ask a question. They're going to try to come up with a strategy to get data that they can answer that question. Then they're going to go ahead and run the lab, collect the data, and then analyze the data. From that data that they analyzed, they're going to come up with an answer, a prediction, and I try to make that a value that can be tested so we can actually measure how accurate their prediction was, and then points are awarded on the accuracy of their prediction. So that's the flavor of this whole thing. Okay, these are the boilerplate type of rules. Team of 2. High protection 4, again, it depends on what we're using, but this is more than enough to cover what I use with. Time limit 15 minutes, and I'm going to use 2 events at the state event that I'm running here in Ohio, and I'll use 2 at the national. It's up to the individual. I think if you go beyond 2 or 3, you're getting into a situation that the kids really don't have time to set up an investigation. They have to go too fast, and therefore it's not in the flavor of what I'm looking for. Okay, the probes this year, and every year it's a little different, but this year I'm using temperature probe, I'm using current probe, and I'm using a voltage probe. So those are the 3 probes that I'm going to use in my competitions, and I'm kind of asking everyone to kind of follow through. Now, I've also tried to plan the event so that if someone didn't have access to technology, they could have the ability to use an alcohol thermometer, or they could use a voltmeter or a amp meter in order to run this, although you'd be at a disadvantage. And at the Nationals, I will definitely supply the probes, and I will be using these probes. The 2 topics I'm going to look at is going to be 2 stations. Topic 1 will be dealing with electrochemistry under standard and non-standard conditions. So that's getting us into our batteries, redox reactions, electroplating, things along that line. And then physical science area, I'm going to be doing things with heat and thermodynamics in both an open and or closed system, kind of in the flavor of keep the heat as an event, except looking at more of the modeling that goes behind that particular topic. Okay, sample labs. Okay, on the national website, and we'll go look at that in a minute, this particular part of the Vernier book, it's Data Quest 1A, gives you the procedure on how to use the Nspire handheld, and it has a couple of real nice warm-up labs that show you how to use the temperature probe, how to use a lot of the menu things. It's something I would recommend any coach to do. It takes minimal equipment to run it. You need an Nspire and a temperature probe that connects to the Nspire either directly or through the Easy Link, but it's a good warm-up lab. In electrochemistry, this is the one that it will do everything. If you do this lab, there's nothing I can throw at you that you wouldn't be able to handle. At the invitational level and the regional level, I will not go near this deep. This would be more at the state level or the national level at this lab, and we're going to look at it later on, but this is the one that's posted on the national website as a good sample lab. This is a Vernier Lab 31. It's one that I use in advanced chemistry or AP chemistry. Energy content of food. Don't know if you've ever done this lab. This is one where you basically take food and you burn it, and the kids love it. It's basically you're taking sources of fuel, and I use things like potato chips and Cheetos and Fritos and anything that contains some oil. Develop a little or make a little food hanger out of a paper clip that you can support this food on. Put a can of water above it, light the fuel, measure the temperature change of the water. From that, using this formula that you see on the board, mass times the heat capacity of water times the change of temperature, calculate how many units of energy went in there, and therefore how much came out of that fuel source, which if it was a snack food, it'd come out of that snack food. And you can substitute a candle or an alcohol burner. But the premise is if water is changing temperature, something is putting energy in. We can monitor how much that energy is by watching how much that water changes. The temperature probe is ideal for doing this monitoring, and from this we can now calculate how much heat came out of whatever we were using to generate the heat. You could also do this in a chemistry lab, looking at enthalpy. A lot of things you can do with this particular thing. We'll come back and visit it in a minute. Really, the scoring is a little different this year. 2012, I did not give a procedure score at the nationals, and at the state event, I'm saying I'm going to put in a procedure. So the score is still 50% based on a right answer, 30% on procedure, and I'll develop a rubric for that. And then content knowledge is that we'll still have some questions on the particular content that can be used to differentiate the score a little. And I want to explain that for a second, Lowell. What happened last year is there were some people who felt that when the whole points were based off of a right answer, it was leaving it too open for someone who just happened to be a very lucky guesser. I don't totally agree with that, but because there were some people that had a concern about that, we decided that the procedure, the methodology on how you got your answer was going to be part of the scoring, so that we could at least reward people who had a logical and a sound experimental approach towards getting that answer, rather than someone who just put down an answer that happened to be close. So that's why we added the procedure, having 30 points or 30%. Also, every probe has precision limitations. So if I was going to say there is a right answer, then I really have to look at how far or how close to that correct answer did you have to be within the precision of that probe, and therefore you still have just as right an answer, even though you were not a perfectly on the right answer. For example, I did a lab a few years ago where they had to identify how many grams of lead was in a sealed container that caused a cart to accelerate up an inclined plane. Well, the right answer might have been 48 grams, but if someone said 49, that might have been equally right simply because of the limitations of the probe that you were using and the data you collected. Well, the minute I give you a block to say this is the right answer, plus or minus 5%, let's say, then I have a lot of ties, because now I have a lot of people who have the right answer if they've done the procedure right. So I needed procedure and content questions to help separate those scores. So that's one of the reasons it's kind of developed this direction. Okay, these websites we're going to visit individually, but again, this is just the PowerPoint I'm looking at right now. Resources, how you can find more information, how you can have more practice labs. The TI website is absolutely full of activities. This is a place you could go. You could download in your subject. You could look for different type of activities, and it's a great place to find additional resources. Vernier, and we'll look at this one in a minute, has all kind of resources download. Products, they got subject areas, they've got experiments that you can go after and get more practice things. Atomic Learning is an incredible tutorial website on just how to use the calculator, and each one of these items you can go look at, and there's a little video clip that you can pause and re-look at and get more comfortable with the actual handheld. And then, of course, the national website. Where you can go and find everything on technical problem solving and Q&As and things like that. So that's the PowerPoint presentation. Then we're going to break out of this and look at the live stuff. And again, there's my contact. Questions at this point, Lowell, do you have any?
Not yet.
Okay. So, pardon?
Can you hear me?
Yeah, I can hear you fine. There's no problem. I told the group yesterday, because they were asking me, do we need to go out and buy a handheld? And I said, you know, I would definitely say that every team is going to have an advantage if they go out and purchase at least one handheld retail-wise, and it's available at a lot of different stores, your Office Max, your Best Buys, your different type of stores that sell educational supplies. And the beauty of it, when you buy a handheld, you get a software that is loaded into a computer, and that software is what you're looking at right now. So it allows me to have an emulator. This computer, you know, this calculator actually works like the handheld, which gives you another tool that you can practice with or let your team practice with. I'm much more comfortable using the mouse on the computer. My students have no problem with the handheld, and so it's a different choice. Different people like different things. Now at the Nationals, they're going to be using the handheld, the smaller unit. So that's what you're looking at right now. Okay, I want to go. Okay, so one of the websites I told you about was this one right here, which is Atomic Learning. And the address on that is just Atomic Learning. I don't know, can you see the address from your screen? I'm not sure what all you see on my screen. Can you see it up here, atomiclearning.com /TI-Nspire? If you go here, this is a free site for you, and for everyone. TI has made the arrangements for this. This tutorial allows you to pick up all the different things that we're going to be talking about in the next 2 hours. If you click on, like down here at the bottom, data collection, collecting using the Vernier Data Quest, analyzing the data, event with entry in the Vernier Data Quest. So if you say, boy, I need more practice on that, you come here, you click on it, it brings up a little video clip. You can't hear the audio from your side, but it's going to walk me through how to do it. It's also showing you the keys as they turn red as they actually are doing the different activity, and it's just a super site to go and maneuver through. So that's Atomic Learning. Vernier is another website, and over here, this is live right now, there's experiments. If I go in experiments, down here it shows. Now they're going to actually have me choose a book, so I can say, okay, I want to do Advanced Chemistry with Vernier. It shows me the book. it shows me a list of the different labs. The lab we're actually going to do is Lab 31, determining Avogadro's number. It tells you you're using a current probe, so over here you can see what probes are done. So if you wanted other practice with maybe a temperature probe or whatever, if I go to Avogadro's number, it gives me the procedure, gives me a kind of a short version of it, shows me the probe, and then I can actually download a preview. So this is a website that has just tons and tons of resources I can go to, and again, it's got all the books. So they make a lot of their resources wide open for you to use. So let me shut that down. And Course Science, Olympiad's website, if you go up here to the events, I'm not sure why this pop-up window is here, but it's right at the wrong place. So if I go to the BC events, technical problem solving is right here. It's right behind that screen. So if I click on that, it takes me to the technical problem solving web page. And then here, and I'm not sure why this isn't updated. I'm going to have to talk and get to 2014 information on here. But this is from last year. It gives you that DataQuest appendix. So if I click on that, it gives me a great resource for how to use the actual software DataQuest, and it's available so you can have a tutorial on that. And these are all, you know, just pretty nice things. Okay, trying to see what else I want to do before I actually start running. Have you seen all these things, or is this new to you? Lowell? Okay, is this new stuff for you, or is this stuff you guys already knew?
New.
Okay. Down here, these are some archive events.
New, have seen it before.
Okay. This voltage probe activity, I didn't even know it was here, but this is a real good one to practice for this year. One of the problems I have, of course, is I try to come up with different levels of events for invitationals that are different from regionals, which are different from states, and then different from nationals. But each of those events staying within the flavor of the description of the station and the probes that we're picking. This particular one right here, voltage probe activity, is one that I think would be really kind of, see if it will open. I got too many windows open on my school computer. It's going to be bullheaded. But what it was is it's basically, okay, I'm going to get out of this. Okay, here it is. It's, let's see if I can get the, okay, so here is where you're using a voltage probe. You're basically making a battery out of a lemon, a potato. They're using the 84 calculator, but this same thing would work with the Nspire. It works exactly the same, works with the same probe, and it's an exploration where you could ask a kid at an invitational, you know, here's some different fruits, what kind of battery can you make, what kind of voltage can you get, how do you optimize that voltage, is it better to use, you know, MacGyver would save the world with a penny and a quarter and a cactus plant. So, you know, you can talk about if you have a handful of change and there's a nickel and a quarter and a penny, is there one that would make a better battery? Is there better fruit to use out of your lunch? And it would be entirely a way to get the kids exposure on using the probe without making it a high-risk type of thing. And part of this at the invitational level is just to get their hands on the equipment and see how it works. So that was a real good activity here, and I didn't even know that it was on this website, but it's a voltage probe activity. It's in the archives. It's for the older ones. 2014 is not up here, so I'll be trying to get that information to Chicago so they can get this updated. Last year's stay tuned and enzymes were last year's activity, so this year it will be the ones I showed on my PowerPoint, the Avogadro's number one, and the energy content of food. So those are just some resources, and I want to clean up this. Okay. I'm closing most of these simply because my computer is running too slow with all this open. Alrighty, so what I'd like to do now is show you a little video clip, and this was done very quickly, so I'm going to narrate this as we go through it, and I'll pause it. This is the wrong one. Hold for a second. I grabbed the wrong one. Okay, so I'm going to go ahead and pause this and let you know what's going on. So if you are an event supervisor and you're going to run the event, through Workshop Loan, you can request the tools that you need to run the event. If you want a lot of help from me on running the event, I am more than willing to write the event at a regional level or at a state level. And of course, I'm going to do the actual state one or the national one. But I will, in that write-up, I will say you need to order, this many voltage probes, you need to order this many temperature probes, you need this many handhelds, this is the equipment you need to run the event. The only thing you'd have to supply me is to let me know how many teams you plan to put in a rotation, because that will control how many pieces of equipment that you have. My personal experience is if I'm running 10 teams, then I'm going to have a couple extra pieces of technology in case something fails, because when you're tied to technology, if you lose a calculator, then you're in trouble. So in that list that I'll give you, I will build in a few extra pieces just to protect you in case something fails. Also, as I write the event, like I told you, I try to think in terms of items that are easy to get. So I may say, hey, sulfuric acid, 1 molar is the ideal solution, but you can substitute vinegar if you need to. So I will probably give you some options to say, here's what I would use, but here are some other things that will still give you a successful activity. So those are things that I can supply you. Lowell, when's your first invitational in Kentucky?
March 1.
Okay, so I've got one coming up in January. So my goal is to have all the write-ups done before Thanksgiving. Does that give you enough time to work with your event supervisors?
Yes.
Okay, so that will be my goal. If you need that information, write me and ask me. And the only thing I've got to do, and I'm going to ask Chicago some guidance on this, is I need to make sure I have, like if you ask me, I'm going to send it to you because I know you're going to get it to the correct people's hands, but I don't want to make it so I would inadvertently send it to a coach thinking that they were an event supervisor or even a student. So I'm going to use at least the state level as my clearinghouse to make sure that these write-ups only get to the appropriate people.
Hey, Mike.
Yes.
We have a question from Elizabeth.
Okay.
And her question is, which voltage probe do you recommend? And then there's a question, the differential voltage probe.
Okay. I have done the event so far using the original voltage probe, which is like around $12. The differential voltage probe should work just fine. So I don't think it's going to be critical which one that you choose. They both should work fine for what I'm doing at least.
Okay. And then we have a second question from Angie, and she just wanted to clarify the only handheld allowed is the TI-Nspire, and that LabQuest will not be used?
Okay, LabQuest will definitely not be used at the national and at Ohio State because, again, I'm running that. It's up to the event supervisor what technology they supply, but the student wouldn't bring their own. The event supervisor would be the one who would make that decision as far as what they choose. An 84 calculator that would accept the same probe, I guess I would like to have that question go into the national for a Q&A and get a reading on that because I'd rather make that a definitive decision that is published. And so I would suggest that that one's sent to Chicago as far as on the Q&A on the website and ask whether an 84 calculator that is carried in by a student, would it be allowed to be used on the data collection portion. And I don't want to make that decision. I'd rather have that one come from Chicago. Did that answer what we needed?
Yeah, I think so, Mike. That's so far all the questions I see.
Okay, and I'll go ahead and run this video, so here it goes. So when you order equipment from Workshop Loan, what is very common is that they'll send you a pack of 10 calculators that comes in its own charging bay. If you want a lab cradle, they come in groups of 5, also in a charging bay. And the important thing to remember about these two, and I'm going to pause this for just a second, is that they come in partially charged. So if you're an event supervisor, you need to open the package. Typically, you get them 2 to 3 days ahead of your event. You need to get them charged. You need to plug them in and give them charge. And when you charge them, there's a little indicator light on the side of it. I think I'm going to show that. You got to make sure that they're gone to green so that you have a full charge. So they're normally in a case. You don't have to do what I'm doing. They're just a matter of a single plug. You plug it in, and the whole case gets charged. So once they come in, there's your indicator lights. They're not going to all be green initially, but once they set overnight, they should be. And there's your indicator lights on your lab cradle. You want them to be green. If you find after a period of time of charging, they still have not turned to the green, sometimes what you have to do is hit the reset button on the back of the calculator, use a pen or a pencil to depress that dot, and then it will typically have no problem charging up. So sometimes it gets into a funny cycle and it doesn't get a full charge. And this is where the reset button is on the cradle. So when you get your equipment, you'll probably get it on Thursday. If you have a Saturday event, open the case, do an inventory, make sure you got everything, get it charged, and make sure everything's showing. Now this is the Easy Link that's used. It can be used in place of the lab cradle. The difference between the lab cradle and the Easy Link is that the lab cradle can have multiple probes at one time, and the Easy Link only has one. Now it's the same probe, it plugs in the same. If I'm doing a temperature lab, probably the Easy Link is the least cumbersome. It's the way I would go. But if I was doing a lab where I was doing something like I wanted to have maybe a current probe and a voltage probe at the same time on, and I wanted them both on the same handheld, then the lab cradle allows you to do multiple probes. I'm going to demonstrate that in a minute. So the advantage of the lab cradle is that you can do multiple probes. The disadvantage of it is it's another piece of equipment you got to work with. The advantage of the Easy Link is it plugs directly in the calculator. The disadvantage is actually two. One, you can only use a single probe, which is fine for most labs. The other disadvantage is that it's using the battery of your calculator, where the lab cradle has its own set of batteries. So when you're using the lab cradle, you have two sets of batteries basically running the probe. And so for some probes, that's really good. For example, if you're doing maybe one of the chem activities, a lot of the chem activities use some more powerful probes like a pH probe or a colorimeter. These are high battery draining type of probes, and so in those events, possibly in water quality or forensics, you might see the lab cradle because it gives you a longer battery life with those probes. For technical problem solving, unless I use multiple probes, I will not use it. The Easy Link is more than adequate for what I'm doing. And again, these are things that a lot of high schools have because they've been around for quite a while. The 84 calculator used the same piece of equipment, so it's not like you have to buy something new for the Nspire. It's the same Easy Link that we've used for several years. And again, the probes that we're using are standard Vernier probes, so they're also ones that you may find in your local high school. I think I'm going to show you the probes at this point, so let me continue playing the video. So the questions that were asked earlier about which voltage probe, I think I want to show that. So this is your standard temperature probe. Okay, so that's what our current probe looks like. The voltage probe looks similar to that. It's got a little bit different connector as far as the wires, and this is the inexpensive, the standard voltage probe that I'm going to use tonight. So that's the probes we're going to be using this year in technical problem solving. Now to connect the probes, you need an interface. The easiest interface is the link that has a mini USB port. You're going to plug it in. There should be a green indicator light that comes on. that lets you know that your battery's good in your calculator. Then, depending on what probe you plug in, okay, once it connects in, the calculator should automatically fire up and know what probe it is. And if you exchange probes, it's going to know you did that. So now I'm going to use a lab cradle. If I'm going to do multiple probes, or I'm using a probe that has a high drain, I put it in. There's a little secure button at the bottom you slide up that just holds the two together. And now the probe does not need the Easy Link. You go directly into these side ports. And I always start at the channel 1. I work from channel 1 to channel 2 to channel 3. They don't have to be the same probe. They can be, 3 different types of probes, or they can be identical probes. The window will fire up, will recognize the probe, and it now knows I got 3 probes. One's looks like voltage, one's current, one's temperature, and it fires up accordingly. So it's a plug and play, which makes it pretty easy for the kids to use, and that's the setup. Okay, so now I'm going to pause this, and what I would like to do is actually try it. So here's what I'm doing. On my calculator, I've got a calculator that, so Lowell, this is something you guys can try. If you've got an Easy Link, and you got a temperature probe, and you got an Nspire calculator. Do you have those in your room?
Yeah, we have them.
Calculator, an Easy Link, and a temperature probe. Okay, so just give me a second. So what I'm going to do is I'm going to take a picture of my calculator. So what I'm doing right now you don't need to do. This is just me. Okay, so what you're seeing right now is what's actually on the calculator in front of me. So everything I do on my calculator, you're going to see. And so when I start out with the calculator, what I'm going to do is I'm going to go to the home key. So you're going to see it turn red. And when you see the home key, this is the screen that you should open up. I'm going to start with a new document. So when I do this, if I've ever used this calculator before, it's going to come up with a screen that's basically going to say, do you want to save? Okay, this one didn't. So let me go ahead and just add a calculator. And don't do this. Don't worry about this. I'm just going to try this again. So go to 1. It's going to give me this screen that says, hey, do you want to save? And this is just a safety screen. You're going to say no. You know I don't want to save this. This is just old information. So in between rotations, when I just had a group of kids come in, and now I've got 10 minutes to set up my room for the next group, I'll go through each of my handhelds that are out there, and I'll go new document, and when it says, do you want to save, I'll say no, and that resets the calculator back to the beginning condition I need to be. So I'm going to say no at this point, and again, I usually have a volunteer do this for me. So I've got one person in my room during a rotation going through and saying no to every calculator to get them back to the beginning. Okay? Now, if I go back to my home screen, and I usually like to start from here, if I take my temperature probe and I connect it into my Easy Link and then connect it into the top of my calculator, if my batteries are good in my calculator, it should fire up and know that it's a temperature probe, and it should go to this screen automatically. And the only thing I'm looking at right now is up here at the top of my screen, there's a little battery indicator, and if that's green, I'm good. If it's yellow or red, this may not happen. So what I would do is, again, having a few extra calculators in the charging bay during a competition, I would swap out that calculator with one that's been charged and just put that one back in the charging bay to increase its charge for the next rotation. So did your calculators open up? Yes.
Sorry, I was just trying to answer a question from Elizabeth, and that is, how many document experiments can you save on the calculator? And then should you clear all the experiments prior to the competition?
Okay, if they come from workshop loan, they've been cleared. So you don't have to worry about that. If they're your own personal calculators, I would probably, if you've used it on something that has collected a lot of data, like a motion detector, I would clear it. Because a motion detector has a tendency of creating a lot of data, and sometimes you do get into memory issues. But if it's coming from workshop loan, that should not be an issue, so they reset those before they send them out. Okay? Lowell, how are we doing? Are we got our calculator up?
Yes, we're doing great.
Okay, so if you play with that one warm-up lab that is on the Science Olympiad website, it's going to say, hey, take this temperature probe and let's do something with it. So if I put my fingers over the end of this probe right now, I'm finding out that, yes, in fact, I am alive. My temperature is going up. And so right now it's working as a digital thermometer, okay? But it's not recording any of this information. It's simply showing you a digital readout. Now, here's something that's very important. When it's in this mode, as far as the calculator is concerned, it is not being used. In 5 minutes, it's going to shut itself off to save the battery. So if you're not actively collecting data and you're just using it to measure temperatures, every 5 minutes you're going to have to hit the on button in order to reactivate it. And I've seen competitions where they use it as a standalone pH meter or standalone colorimeter just to read values. And that's okay as long as you know that at 5 minutes you're going to have to hit on again, and it will default back to its original program. So for example, if you look at the screen right now, it's saying 2 samples/seconds, duration 180 seconds. So that's the default program for this particular probe. If I had changed that to something different because of what I wanted to do, and it's cycled, it's going to take itself back to this default setting. And I saw this happen in one competition where they had used a colorimeter. They had changed its wavelengths to a different wavelength for the competition, but because they were not collecting data, it cycled and went back to the default, which was the wrong wavelength. And so the kids in the competition were not getting the correct answers because they didn't know that they were on the wrong setting. So my personal feeling is I have a sheet of paper that I print out as part of the competition that tells the kids what settings they need to be on so that they can be in control of their own data collection rather than the supervisor having to do all this. And I'll be glad to make that sheet up for you for whatever we're doing. So, for example, I'm going to do a lab right now where maybe 2 samples a second is too fast, or 180 seconds is too long. And if I want to change any of that, it's real easy to do by going to the menu button on the calculator. So you see it on the right side of your calculator at the top, and I'll press it right now and it turned red. If you see that, that's the menu button. And the menu button operates contextually on the window that it's open on. So since we're in the experiment window, it's looking at menu selections that are appropriate for experimentation. So I'm on experiment, which is number 1, so I'm just going to use my right arrow, which is on my touchpad, and I'm going to go over there. It gives me options on the experiment. One of the things I can change is collection setup, choice number 8. Now, what I typically do is I just press the number 8 to go down there, but you can use your down arrow and go down there one at a time, but I find it better just to hit 8. It's more sure. So now I'm on collection setup, and this is where now I can change things. So if I say, well, gee, I want to do it every 1 second, or I want to do it every 5 seconds, I would change it here. And if you see right now, it says samples per second. If I use the right arrow and go over, another option I have is seconds per sample rather than samples per second. So I can make this duration much longer. So I'm just going to go ahead and I'm going to go up and say, okay, I want to do seconds per sample. I'm going to hit enter, which selects it. On my calculator, I'm going to press the tab button, which now turned red. And now I went down to the number of seconds per sample. I'm going to change that to 1. So, okay, I'm going to do a sample every 1 second. I'm going to tab down to the 180, and I'm going to say, gee, 3 minutes is way too long. I'm just going to do a 60-second lab, so I'm going to change it to 60 seconds. Tab on down. The next things we're not going to use, and I'm not going to try to make this forever, so we're just going to go all the way down to where it says OK, and I'm going to say OK, and we've just changed the program. So now it's going to sample 1 second one sample every second, and it's going to run this lab for 60 seconds. And now if I simply hit, okay, now this is a choice I have. If I run my finger over the what do you call it, the center touchpad. It actually is a touchpad, and it's not just a clicker, so I can take my arrow anywhere I want on this screen. But it's kind of like a touchpad on a computer. It takes a little bit getting used to. I personally like using the tab button better. So if I tab the button and I hit tab, across the top I have an icon that looks like a graph. I got an icon that looks like a data table. I have the center section highlighted. When I hit it one more time, I've now got my play button highlighted. I find it a lot easier to start and stop labs using the tab button. Now all I have to do is hit the enter button on my calculator and it's going to start. The kids like the touchpads, but either one would work. It's your call. So now I'm going to go ahead and hit enter, which I'm now starting my lab, and my graph automatically appears. My temperature probe is showing what temperature it's reading digitally on the side, and I'm going to put it in what used to be a semi-warm cup of coffee I had sitting here, so my temperature probe is going up. I'm showing a rise in temperature. Okay, I take it out, and now it's going to start cooling. And so that activity 1A that was in the Vernier book is just basically this. Play with the probe, just see how it works, how it collects data. If at this moment I decide that 60 seconds is not going to be long enough, if I go to the menu selection on my calculator and go to experiment number 1, one of the options I have is number 5, which says extend the collection. So if I go to 5, it automatically lengthened me out to 90 seconds. If that wasn't enough, I can go to menu, I can go to experiment number 1, I can do extend, and now it goes out to 135 seconds. And I can do this, I think, up to 5 times. So if you're ever running a lab and you found out that you didn't give it enough time as an operator, it's very easy just to extend that lab so you keep collecting data without interrupting it. If at this point it's more than enough data and I'm saying, okay, I want to stop, this is it, the play button has now turned to a stop button. If you notice, it's still highlighted, so by hitting enter, or I could have taken my cursor and gone down to the stop button, hit on top, and hit stop. It immediately stops the data collection. It adjusts the window for what I just looked at, and I've got the data that I just collected. So this could have been a real investigation where I was doing one of the labs at the activity, or it could have just be a matter of me playing with it. So Lowell, were you able to do that? Michael, have you had any questions while I'm waiting for Lowell to get back to me?
I have not. I think so far so good.
Okay. Lowell,
Okay.
how are you doing?
Good.
Good. So you were able to collect some data?
Yes.
Okay. Now, I guess the aspect I want to show you right now is that it was very easy to collect data. You plugged in the probe, you started it, you made some adjustments on the menu if you didn't like the default, and then you ran the lab. I mean, that was a piece of cake, I think. I mean, maybe I'm making it seem too easy, but it seems like that was the easy part. Now, the hard part comes with what do I do with it now that I've got it. Okay? Now, representation-wise, at the very top of my screen, I've got a little icon that looks like a gauge. I've got an icon that looks like a graph. I got an icon that looks like a table. Do you see those three?
Yes.
Okay, if I go over to the one that looks like a, well, no, before I go there, back up. Do you notice that right now my play button is highlighted? I'm going to hit tab one time and this file cabinet is now highlighted. Do you see that? I'm going to press that file cabinet before I do anything. So when I press that, two things happened. One, the data I just collected got protected, so I'm not going to lose it. Second, it set itself up ready to do another run. Had I not done that, and I started the play button again, it would have erased all that data without asking me. It would have simply assumed that the data was no longer needed, and I would have lost it all. So one of the things I train my kids to do is when you're done with a run, even if you're not going to do another one, save it so it's protected. Now, if I was going to do multiple runs and I wanted to analyze the data after I ran them all, I could save it like I just did and then start another run. So I could go right now and say, okay, let's just go ahead and run number 2, and I start collecting the data, and I do something different. Okay, at this point my coffee's probably cooled a lot more, so I don't know if I'm going to get as much of a jump. Well, of course the window is readjusted, so it looks like I've really got a great jump going on. And I say, okay, that's a wonderful lab. I'm done with that data, so I'm going to stop it. So I'm going to hit the stop button. I'm going to go to my file cabinet, and I'm going to save it. And now run 1 and 2 are both saved, and I'm ready to do run 3. So I can do run 3. I can do, you know, as many runs as I are interested. Now, if I go up to the top of my screen where it says run 3, and I put my arrow on top of it, and I go ahead and select it, it gives me some options. It says, well, you want to see run 1 again? By hitting enter, I've now selected run 1, and there it is again. If I press run 1 and I go down to run 2, I can see run 2 again by hitting enter. And if I want to see run 1 and run 2 together, because maybe I want to go to more. And I want to say, you know, I'd like to see run 1 and run 2. Oh, wait a minute. So I'm going to click run 1 and run 2, and now say OK. Now I have the 2 runs on the graph at the same time. So this is a great feature if I'm wanting to do some comparison type things, like I was making a battery out of a lemon and making a battery out of a lime, and I wanted to compare the voltage over a period of time or the current over a period of time. I've got a comparison, and I could write questions that I could either be very mathematically aimed, or I could be just conceptually aimed. So this gives you the ability to do it. So that's the file cabinet. So the play button is here. When I run it, I've got a file cabinet that's at this location, and that allows me to save my data, and then kids can do that multiple times. At the very beginning, when I go to a new document and it says, do you want to save, and I say no, all that's cleaned out. So you don't have to worry about the next rotation coming in with that information. So by saying no, you've lost all that information. Okay? Now the icon I was going to when I wanted to show you that is this one that looks like a table. So if I click on that, that now gives me all the data we just collected in a table form. So I'm going to click inside of one of these cells, and so that would be the time, that's the temperature, this is run 1, that's the time, and that's the temperature on run 2. So during that run, as I go down there, this is all the data was collected. So I could numerically go in here and say, okay, what was the temperature, you know, at 18 seconds, or if I wanted to know the highest temperature and the lowest temperature, I could go down through this chart and look for the highest and the lowest values. So it gives the student the ability to look at it in a tabular form, or I can go back up to the graph and I could explore it on the graph itself by clicking on the graph and then using my right and left arrow. I can walk along this graph and I can now say, okay, on the blue graph, I'm at 29.4 degrees, and on the red graph, I'm at 27.5, and my time is 18 seconds. So I can explore the graph just walking on the graph itself by clicking on the graph and then using my right and left arrow, or I can go up to the icon that looks like a table, and I can go in there and explore the table by looking at values. So there's different ways you can get this information you just collected. So are we still good?
Mike, we're good on my end.
I'm sorry, what?
We're good on my end.
Okay, you're good on your end. Sorry about that. I didn't understand you. Okay, Lowell, are you still good?
Yes.
Okay. Now, what we've done so far is we just plugged in a probe. We adjusted the settings on the collection mode. We've ran a couple runs. We've saved the information so we could go back and analyze it at a later time. we looked at a very simple analysis where I was simply looking for values. What was the highest value? What was the lowest value? So if I was looking for a change of temperature, a delta T, this may have been enough. I might have just simply said, okay, what's the highest, what's the lowest? I can subtract that and calculate how much energy was exchanged based on that equation. But let's say I want to do a more in-depth analysis of this. So one of the things I can do now is I'm going to go back to the menu key, and I've looked at the experiment. That's where I changed the time. I haven't looked at the analysis key, number 4. So if I go to choice 4, and I'm going to go down to 4, and I'm going to use my right arrow, and again, I could have simply hit the number 4. Things I can do here, okay, statistics, curve fits, modeling, there's a lot of neat stuff here. But this is where I'm going to use more of the power of the calculator to help me quickly do something. So let me show you how I would do that. So I'm going to go back to my graphs. I'm going to hit escape on my calculator twice, which gets me out of that window the first time. Escape again gets me out of this window. I'm going to go to this graph and say, you know, it looks like there's some type of cooling curve going over here. I'd like to know what's going on, but I really don't want to confuse myself with this data over here at the very beginning. So what I'm going to do is I'm going to click on the screen once I started doing a cooling curve. And when I get that arrow that looks vertical, I'm holding down the click button right now. I'm going to now drag my finger to the right, and I'm selecting a portion of the graph. And if I say, okay, that's the portion I'm interested in, and then if I click again, the calculator has now said, okay, I'm only going to look at the data between those two vertical lines. And now when I ask it questions on the analyze portion, it's only going to answer those questions as it relates to that data. So I can have good data and bad data on the same trial. Now I can select the area I'm interested in and only analyze that, which means I don't have to rerun that run to try to get perfect data. I've got some good stuff here. Why do I want anything better than this? So then once I've done that, if I go back to menu.
Question?
Yes.
A little confusion on how when you say slide.
Okay. What I'm literally doing when I held down, let me see if I can get out of this. And of course, Lowell, you know, this isn't easy for me either. The kids make this look easy, and I always have a hard time. And I just did it very well, and you're going to make me do it again. I'm on top of the blue line. You see my arrow?
Yeah.
I'm holding down the center click button. I've got that vertical line. Now I'm simply releasing some of the pressure and dragging my finger on the touchpad to the right. And I haven't selected my area yet because it's still ready for me to click a second time to say what area are you interested in. Now by clicking a second time, I've now locked that in. Yeah, I lost it. Okay, let me try one more time. So I'll click it, slide it, and then click it again. And now I've got my two vertical lines fixed. So it takes a little practice. And again, during the competition, it's not when you want your kid practicing this. He wants to have done this some before. So he's collected some data. Click and hold down until you get the vertical line, and then release a little pressure and slide my finger on the touchpad, and I'll drag that vertical line over until I have the area I'm interested in. Click it again, and that locks that area in. It takes a little practice. It's real easy to do on a smart board, to be honest with you, but that's why I'm doing this on the handheld. I want to try to do it the way you're doing it. Now, once I've selected it, and I go back to the menu, and I go back to Analyze, and I say I want to do a curve fit, like number 6, then it's only looking at that area. Or if I said I want to do statistics, number 5, it's only looking at that area. Okay? So if I would do statistics number 5, it wants to know which run. I want to do run number 1, so I'm going to select number 1. Then the statistics it does is it says, hey, in that window you just gave me, the minimum value was, the maximum value was, the average value was. And so this information, if I just say okay and get this window closed, is recorded over here on the side. So here is the minimum, there's the maximum. I can take my drop arrow here. And I'm even getting deviations. So I can look at the min, the max, the mean value and the standard deviation. So if I wanted to do some type of more in-depth analysis, I've got all that information there. The brackets over here are showing you where it is I selected. I went from this bracket to this bracket. So that's what that information is pertinent to. So if I wanted to max and min to do a delta T, I could either go through that list and look for the max and min, or I could simply have selected that area and said, hey, give me the max and min, and I could have used the power of the calculator to get that answer quicker. And again, I could do this with an alcohol thermometer, but this is giving me a more efficient way of getting there. Okay? Lowell, you're still trying to select, or did you make it through that part?
I think we're good on that.
Okay. So I can pick good data from bad data. I can analyze it. The analysis could have gone as far as I could have said, hey, I actually want to do a curve fit. If I'm going to go to a menu and go to an analysis and do a curve fit, it's going to ask me the same question, which run am I looking at? I'm going to say run 1, and then it's going to give me all kind of options. So now it's up to the student. Does that look linear? Is that a quadratic? Is that, you know, what model is that? So this takes some math knowledge. This isn't just a automatic, it's going to do it for you. You've got to make some decisions. And if I said, okay, I think this is exponential, choice number 6, it's not going to argue with me and say, no, it isn't. It's going to do it and do the best it can. So if I pick number 6 right now, it's going to give me the fit. Again, all this information is already recorded to the side, so I can either read this by going down in this window, and it gives me the equation AB to the X. I've got the values A, B, R, and R squared, and the R value is going to give me an indication on how good that fit is. I can close this window, and all that information was recorded here on the side, so it gives me my exponential, gives me my A value, my B value, my R value, and visually, the black line here on this graph is my equation, and the blue line is my data, so then the student has to make a decision whether he thought that was a good fit or not based on multiple levels. Visually, did it look good, or mathematically, did the R values indicate it was a good fit? And these are things that the student has to decide whether that model is the one he wants to use to make the ultimate prediction that the event is going to ask him to make. Because if he has the wrong model, he's going to make a wrong prediction. So that's the calculator. Now what I'd like to do is I'd like to actually run a lab real quick, and let's see what it looks like. So what I'm going to do, and again, I'm going to try the hands-free microphone. I don't know if it's going to work or not. I've got a coffee pot that's got some hot water in it. I've got a styrofoam cup that's got some cold water in it. And I've got a temperature probe. I've got 2 temperature probes in my cradle. The one temperature probe will be showing me the temperature of the hot water. The other temperature probe will show me the temperature of the cold water. I'm going to literally just dump some of the hot water into the cold water and let both probes watch what's going on. And I'm going to collect that data, and then I'm going to go ahead and try to analyze what went on. Okay, so I got 1 cup with hot water, 1 cup with cold water. I will start the data collection so that we can see the initial temperatures of those without mixing them, and then I'll mix them together, allowing the temperature probe to go be both together, so we'll actually see what both probes are doing at the same time. I have measured out the cold water. I put 100 grams of cold water in my styrofoam cup. I'm deliberately not massing out the hot water. I will know its temperature. I will not know how many grams of it I've added to the cold water, because that could become the whole point of the investigation. What was the mass that I added? There's now a right value I could get by massing the cup afterwards. The student could calculate that based on the data, and then I could measure how accurate they were based on my known value. Okay, so that would be maybe a level towards a regional level where I've got a known value. We're using temperature, and we're using the concept that something's losing heat, something's gaining heat, but if it's in a closed system, the total heat has to be accounted for, so we ought to be able to do some math. So I'm going to go ahead and switch over to a different calculator so you can see that, and I'll be back on the phone in about 2 minutes. It shouldn't take me very long. Yes?
Before you switch over, Tim has a question, and the question is, if the student decides that they've chosen the wrong model, how do you delete the black line and choose a new model?
Very good. Thank you for stopping me. Okay, if I go back to menu on this one, and I go back to analyze, choice number 4, how I got there to begin with, and I go to curve fit, which is what I did before, and I go to 6, okay, and run 1, which is 1. Okay, I was expecting to see it say run the model. That may have been on something different, so let me look at that. Okay, let me remove number 8. There it is. I knew it was there somewhere, so I went to, let me back up. Let me get there so that you don't get lost with me. I went to menu. I went to analyze, number 4. Number 8 says remove. So I'm going down to number 8, and it removes the exponential, which is choice number 2. And there it is, it's gone. Okay, so I hope that helps you. I'm sorry it took me a while to find it, but I knew it was there somewhere. All right, we good? Okay, so what I'm going to do now is I'm going to switch this presentation off, and I've got to switch over. So give me a second, and I'll be on in a second. Okay, a little technical problem at this end, but I think I'm back on control. So what I've got right now is I've got a temperature probe that's in hot water. It's showing 37.3. I've got a second temperature probe in cold water, which is 21.2. I've masked the cold water. I know exactly that I've got 100 grams of that. I don't know how much hot water I put in a second styrofoam cup that I've got the temperature probe in. So what I'm going to do now is, this is a 3-minute lab. I'm going to leave the setup exactly like the default was, so I'm not changing anything. I'm going to start collecting the data while the two waters are separate so that I have some baseline information, and then I'm going to pour the hot water into the cold water and transfer the probe from the hot water into the cold water also, so we'll see both probes together, and then we're going to watch what's happening. So again, I'm going to set the phone down and walk across the room and get that started. So we'll start the data collection in about 5 seconds.
You're going to try to use 2 probes at one time. You need that other box, the other control. What I've given you only works with 1 probe at a time.
Okay, at this point, I've put them together. I've transferred the hot water into the smaller cup, and we're watching the 2 temperatures. Now, the lab is going to run for 3 minutes if I let it go that far, but, you know, once that I have received, you know, they've reached equal temperature, I can stop it at any point, but I'm going to let it run just a little bit longer. So the setup for this was, I had some hot water. Didn't know the starting temperature. I had an old coffee pot that I plugged in and filled with hot water. I have some styrofoam cups. I had some room temperature water, a graduate cylinder to measure out the cold water, and I've got a scale so that I can verify the final amount. So I'm going to let this go a little bit farther. I think at this point you can see that I've reached an equal temperature, so I can go ahead and stop the graph. And when I stop the graph, the first thing I'm going to do is go to the file cabinet and preserve the data by saving it, and then I'll go back and I'll reopen the window so I can then analyze the data. So I'm going to walk across one more time and shut it off and then save it and then be back on the phone. All right, so Lowell, did you see what I did? Were you able to follow that all right?
Let me ask the people here. Okay?
Okay.
We're okay?
Now, I added hot water to cold water. The unknown right now is how much hot water did I add. I could have added an ice cube, and I could have added how much ice did I add. I could have added a hot piece of metal, you know, any of the specific heat types of activities I could have done, and they all would have shown me the cold water heating up. Now, the second temperature probe wouldn't have been available if I had a hot piece of metal, because I can't put a probe in the metal or in the ice cube. So I would have assumed that a temperature probe in the water where the metal was being heated was showing me the beginning temperature, and I wouldn't be able to follow this blue line coming down here, but at least I could follow the brown line. I could follow the cold water and do all the calculations. So you can do this thing with different sources of heat, is the point. All right, so now what is it I want to know? I would like to know how much temperature did the hot water lose and how much temperature did the cold water gain. So I'm going to look at my data, and I need to get some information. So one of the ways I can do it is by taking my cursor and simply go up here and say, okay, what was the starting value? So I can click on my graph, and by walking on it, I can see that it's 7 seconds, or I can go back as close to, pretty close to 0. I can see that my starting temperature on my hot was 36.9, and my cold was 21.2. I could have also got that information by going to my table, clicking on that, and seeing that at the temperature at time 0 is actually 37 on temperature 1 and 21.2 on that. So I can get my data from my table, or I can get my table or my data from my graph. If I wanted to deal with the reality that probably that temperature was changing on both of those at the beginning, I could go in here and say, okay, what if I select my data up here and drag it over to about here. I don't think I got it, so let me try it again. And then go to my menu and analyze and do some statistics on run 1. I would find that my mean temperature was 36.85 rather than 36.9, or it would be 36.9 to 1 sig or to the 3 sig figs. So I could also do some statistical analysis of that level, that plateau at the beginning, and do this same thing with the other one. So I could then, multiple ways I could get a starting value. I could do it by looking at the graph, looking at a single value in the column, or do an average of a zone on the column, that plateau area. Same thing I could do with the, what was my final temperature? I could come down here and say, well, let's go down here and go from about here to here. And let's do analysis of that. So I'm going to go menu. I'm going to go to analyze. I'm going to go to statistics. It shouldn't make a difference whether it's run 1 or run 2. I'll just pick run 1. And it's going to tell you that my mean value now is 28.2, so that's my ending temperature. My hot water went from 36.9 down to 28.2. My cold water went from 28.2 up to from 21.2 up to 28.2. So that's my data that I got. So I collected it. The lab took, I don't know, less than 2 minutes. And then if I'm going to do analysis on this thing, I'm basically going to say, okay, so the heat loss, and I got to remember how this is. I got to okay, can you see that writing? It's asking me questions on my end, and I'm not sure if it asked you or not. So Q equals M C sub P delta T. Are you seeing that?
Yep.
Yes.
Okay. So what I'm looking at is the hot water started at 36.9. The cold water started at 21.2. Cold water's going up. The hot water's going down. The final temperature was my 28.2. And then I can say, okay, using this thing, and I can set up that Q loss equals Q gain. The one that lost the water is going to be the mass that I don't know. It's water, so it's 1 calorie per gram per Celsius degree. And the change of temperature is going to be 36.9 minus, you guys know how to do all this, 28.2. That would be my heat loss. I'd set that equal to my heat gain, which is the 100 grams of water that was in my can, or in my container at first, times the same 1 calorie per gram per Celsius degree, times the change of temperature there is going to be 28.2 minus the 21.2. And from that, I ought to be able to calculate what my mass is, and then I can verify it with a scale. So it's an easy lab to do. I would consider that more of a regional level of difficulty. I could replace the water with a piece of metal, and so now maybe the C sub P is the unknown value that I have to go for. I can use that C sub P value to do an identification of the metal, or if I want to use an alloy, I could actually do a percentage composition of that metal. So it becomes a pretty wide lab that I can do, and all I did was collect some temperature data and throw it into a heat loss equals heat gain equation. So does that make sense?
Yes.
Hey, Mike, before you get too much further down the road here, there was a question that was asked earlier, and that actually we have two questions. One was, from what you were working on previously, what if a student wants to, sorry, I'm just going to read this verbatim. My student wants to know if she can first use one option to analyze the data and then decide to use another just to see which fits her need better, and then decide to keep one analysis.
Okay, so when we did the analysis, I could have gone back and given it I could have done it 2 or 3 different analyses. Now my graph is going to get kind of messy looking because they're all going to be on that screen at the same time. But then I can go back to analysis, and on that number 8, remove, it gives me the options of which ones I want to remove. So then I can go back and remove the ones I don't want anymore because I figured that another one works better.
Great.
Okay.
And then the second question, I'm not sure if you're going to cover this again later. Is there more information on the scoring rubric anywhere? How do we explain accuracy and procedure, and what students need to include in their answer to make it reach these goals? Any kind of example will be really helpful.
I will be writing that, and that's what I'm shooting for by the Thanksgiving time, to have that posted before the first invitationals. So that is a goal. I do not have it yet, but I understand the need for it.
Great, thank you.
Okay. Now, 2 more things I want to show, and I'm watching the clock. It never seems like there's enough time. This was a lot of information for the temperature one, and at the same time it showed you that it's a matter of just choosing the probe, selecting the parameters that you want to collect the data, and then once you got the data, it's knowing what to do with the data. And there's power in this calculator as far as how to analyze it. The atomic learning has a lot more analysis you can do, and you can look into that. I find at my school, my math teachers are a tremendous resource to use to look at a more in-depth analysis of this data, or some quick tools that they can use. But you could get this by simply going through the graph, going through the data table, looking for values, and understand that what you're looking for is a heat loss and a heat gain type of thing. What I want to do is say, well, what if time isn't what I'm looking for? What if I want to take a reading, I want to change something, then I want to take another reading, and I want to see if there's some type of pattern going on. So what I did is I said, okay, again, this would be more of an invitational level. What if I said, okay, I've got this lemon, and I want to make a battery out of it, and I want to know whether this battery is improved by my location of where I put the probes into this lemon juice, or whether different materials would make a better source of battery. And so I've got some things I want to vary. I want to find out if a lime is better than a potato, is better than an apple, is better than a grapefruit. You know, I have different things I want to do. So a time graph is not what I'm interested in. I'm looking at an event, and I want to get a reading, and then I want to compare that to another event, and then eventually I want to make some type of conclusion. So what I'm going to go right now and gather from another table is I've got a lemon, and I've got 2 nails I got from a hardware store that were made out of different materials, and I got my voltage probe. And I'm not using a cradle, I'm simply using the Easy Link. So I'm going to go gather that material and bring it up to where I'm setting by the smart board. So if you want to get that, Lowell, what I'm looking for is a lemon, 2 different types of metal, my voltage probe, and my Easy Link. So that's the equipment I'm going to go gather, and I'll be back in about 30 seconds. So glad I got this hand-free microphone that I can't use. All right. So now on my calculator, I'm now taking off the temperature probe. I'm going to go to the house. I'm going to plug in my Easy Link that now has a voltage probe on it, and what I have is the inexpensive voltage probe, the one with the 2 little banana clips at the end. I'm going to go to the house and say, okay, I want a new document. It's going to say what it always says, you want to save. Again, I'm done with that data, so I'm going to say no. And then I'm going to add the Vernier Data Quest app, which is number 7. If at your competition, if you have 2 calculators supplied at each station, you can have one calculator that has a temperature probe on it, a second calculator that has a voltage probe on it, and then you don't have to do this because the calculator will already know it's a temperature or know it's a voltage, and they don't have to spend time switching from one probe to another. For a practice at your team type of thing, this is how you would do it. So you just simply put in the new probe, tell it not to save the old data, and if it doesn't launch itself on a voltage probe, you go down to Add Vernier Data Quest number 7, and it will do it. So if I go to 7, it's going to say, okay, I know what you're doing. It's going to look at what probe I put on, and it's going to show me the probe. So at competition, I would have 2 calculators at each station. So from workshop alone, I would be requesting at least 2 calculators for the multiple stations that I was going to set up, and then a couple extra, knowing that they come in banks of 10, just to have your protection. I think the package they send you has 30 calculators in it, which if you're running a rotation of 10 teams, that gives you 10 extra calculators. You should be in great shape. All right, so now the voltage that it's showing right now is a voltage that's an internal voltage. It doesn't mean anything. If I would connect it, the black lead to the red lead and basically short it out, then it's going to go down to a 0 voltage, or it should be zeroed out right now. So if I want to zero this, I would go to Menu. I would go to Experiment, choice number 1. I'd go to Set up Sensors, number 9. And I would zero it out, number 3. And it says, okay, this right now shouldn't be showing any voltage because I've got the red lead and the black lead touching each other. If I disconnect them from each other, it's going to show me internal voltage again. So don't let that number fool you. Now, what I am going to do on this one is I'm going to say, okay, I've got 2 dissimilar metals. And what I did is I got a galvanized nail that you would use for exterior carpentry work. And then at my particular store, they had copper nails that they use for putting slate shingles on a roof. So I got a copper nail and a galvanized nail. So I should be able to create a battery out of that. So if I put the nail into my lemon in one location, put the other nail in another location, and then I click my voltage probes, one on each nail. So I'm putting the red one on the copper, and I'm putting the black one on the zinc. I'm seeing I have a voltage right now of about 1.26 volts. Now, what if I had hooked them backwards? So let's take the black one, and I'm connecting it to the copper, and I'm putting the red one to the zinc, and I should get, I was expecting to get the same voltage, but on a negative because I've got them backwards. So if you would hook this up backwards, the point I wanted to make was you're not going to hurt the probe. You're not going to cause damage to anything. You're simply going to get a negative voltage. So I know at this point that my red lead needs to go to my copper, which makes it the cathode, the positive terminal, and my zinc becomes my negative, which is my anode. So I could do a very simple lab like this and say that I'm going to organize these in order of activity, which metal is going to donate the electron to what other metal, and I could do an investigation if I had several different things and say organize this list in order from lowest to highest based on the activity list. And you could find out quickly that zinc is more active. That's why it had to be the negative terminal. Now, the investigation I'm going to do here is I want to know if I put this copper nail somewhere different in the same lemon, does it change the voltage? Can I make this voltage go higher? Can I make it go lower? You know, what determines the voltage? So I want to take several readings on the same lemon, and I want to see if the voltage is going to change. And I don't want to do a time graph because I'm not trying to do this on some type of time mechanism. I just want to try different combinations of distances and see what that does. So the default program is not correct this time. 10 samples per second for 15 seconds is not going to do what I needed it to do. So I'm going to change the menu. But I'm not going to change it with a time. I'm going to change it with an event. So this is different. This is something I haven't done yet. So I'm going to go to my menu, which again is contextually interpreted based on the window I'm on. I'm going to go to experiment, which is choice number 1. This time I'm doing the collection mode, number 7. So I don't like a time graph. I want a different type of collection. So I'm going to go to choice number 7. And it says, okay, time graph is what you've been doing. What do you want to do? Well, the one I'm interested in is number 2, event with entry. We won't worry about the other ones right now. But event with entry, now, as I select it, says, okay, what is this event? Well, I'm going to use the event distance. So I'm going to type in DIST. And I'm going to tab down to units, and I'm going to do this in centimeters. So I'm going to tab down to OK. I don't care about the other stuff, and I'm going to say OK. Now on my home graph, or on my home screen, it's changed. It says event with entry, and it says the event name is distance, and my units are centimeters. Okay? So this would be any type of data collection where I want to take some data, then I want to change the parameters, I want to change things, and then I want to take another data point, and then I want to change things again, and I'm looking for, is there something going on? Is there some type of pattern? Is there some type of variation going on? I would use this in like a colorimeter lab where I have different concentrations I want to read. I would do this in a pH lab where I was going to do a titration where I had a pH and then I wanted to add so much base and I wanted to see what the new pH was. Anything that you're going to physically change something and you don't want time to be running while you're doing this. So this is a different type of collection mode. So now I'm going to go ahead and go to my play button. So I'm going to tab around until I get the play button highlighted. I'm going to hit enter. And it does not record the data, it just shows me the data. So right now, that little blue dot is just floating in midair because it doesn't know where to place itself. So if I watch the potential and I see that those numbers are somewhat stable, and again, this is a great place to have discussion with your students on the sensitivity of a probe. The fact that the numbers are changing is not meaning that it's not a good probe. It's simply showing the sensitivity of the probe and where it can't make its mind up. So these values, 0.73, 0.74, 0.72, to this probe is all the same value. And therefore, within my plus or minus, my limitations, I got to understand that all those values are equal. And it's changing quite a bit right now. So what I'm going to do is at the point that I think it's stabilized, there now appears a new icon on my window. If you look here where the play button was, it's now stopped. I now have a third icon I've never had before, which looks like a camera. This is a snapshot. This is going to collect my data. When I'm ready, I'm going to use that button. And this is not, the file cabinet is not highlighted yet because I'm still running the lab. It will not become highlighted until I take and hit the stop button, which then will bring it out so I can save my data. So I'm going to collect my data. So I'm going to collect it. By pressing the camera, and it comes back and says, well, what is that? Well, what I did on my lemon before I got started is I took a ruler and it made a series of black marks, each being 1 centimeter apart. So right now, I've got my probes 3 centimeters apart from each other. And what I'm looking for is whether the location would affect my voltage. So I'm going to type in 3 right now because I want to know that, hey, this is 3 centimeters apart. And I'm going to tab down to OK. And when I hit OK, by hitting enter, it now, that second blue dot to the left is now the recorded value. And again, the one in the middle is still the old one that's saying, yeah, where do you want me to do now? So I'm going to pull my galvanized nail out, and I'm now going to place it 5 centimeters from the copper one. I'm going to watch my voltage. I don't see the numbers changing that much, so I'm going to go ahead and I'm going to hit the snapshot again. and take another data point, and it says, well, what was that? And I said, well, that was 5 centimeters apart. So I'm going to tab down to OK, and I'm going to hit Enter. And now I'm going to take the copper nail out, and I'm going to take it out to the 7 mark. And my probe's just disconnected, so I don't want any of those values yet. So I reconnected them, and I watched my values. I said, okay, it's now stabilized. So I'm going to go to my snapshot. And it says, what was that? And I'm going to say, well, that was 7 apart. So I'm going to tab down. I'm going to say, okay. And this is typically when my kids say, you know, hey, Mr. Smith, how many data points do we need? And my answer is always the same, enough, until you see the pattern. You're looking for what's going on. So I'm going to go ahead and take another because 3 may not be enough. So I'll go ahead, and now I am 1, 2, 3, 4, 5, 6. So I'm now 8 apart. Let my voltage stabilize. I want to hit Tab, or I'm going to hit Snapshot. I'm now going to tell it it's 8 apart, and I'll say OK. And I'm going to do one more, and this time I'm going to bring them within 1 centimeter of each other. So I'm trying to make sure they don't touch. I'm now 1 centimeter apart. Interesting. So now I'm going to collect it. I'm going to tell it it's now 1 centimeter apart. Okay? And at this point, I think, okay, I see enough. I see what's going on. I can now hit the stop button. So I'm going to go over to stop. I'm going to go immediately to my file cabinet and save it so I don't take a chance of losing it. I'm going to go back up here to where it says Run 2. And I'm going to reopen Run 1 so I can look at my data. And now I got to decide what to do with it. So my investigation may have been, is the location of the electrode important to determine the voltage out of a lemon or in any type of object I want to play with, what kind of electrolyte I want to look at. And then part of my write-up would be justify your answer. And so, you know, again, he can go up here and look at the data table itself and look at the numbers. You know, was 4 data points sufficient? Did something just interesting happen at the 1 centimeter? Do I need to go back and collect some more data? Breaking it down even more in that lower area. This is where the experimental method becomes an important part of the rubric on what was the plan and how did they handle the data they got. So each of these different events are being weighed against the other event, and time was not the issue. Time was not what I was looking for. I wanted event. So I had to note event 1, event 2, event 3. In this case, it was distance apart, but it could have been a lemon, a lime, a potato, an apple. You know, it could have been pH ranges. I could have had something that was very acidic and something that was less acidic. I could have compared orange juice to apple juice to grapefruit juice to lime juice and see if it was a pH factor or if it was, you know, what was the issues. So this is a invitational type of event where I could play, and the data is not going to be as quantitative, but again, it's getting the student interested in using the probe and collecting data and the experimental method itself. So it's similar to that one that was on the Science Olympiad website on making batteries out of different materials. And it's using event with entry as our data mode and interpretation. We still okay, Lowell?
Okay.
All right. Now what I'm going to do is I'm going to switch over to Avogadro's number because that's one that's got a little bit more power to it, and I want to show you another thing the calculator can do that's pretty nifty. So what I'm going to do at this point is I'm going to grab a lantern battery. I'm going to get 2 electrodes. I've got a strip of copper and a strip of zinc. I've got a beaker that I've got 1 molar sulfuric acid in it. I've got the current probe, and I'm using the lab cradle. And the reason I'm using the lab cradle is because if I had chose to use the voltage probe at the same time with the current probe, I could have had 2 probes hooked up, and I could have measured voltages as well as current. I could have done this lab if I was only going to use the current probe using the easy link, and then I wouldn't need the Cradle, but I've got the Cradle on this for that reason. The basis of this lab is when I hook the copper and zinc together, I'm going to create a electrochemical cell. If I don't have a battery in there, it's basically I made a battery. If I put a battery in there and I reverse the terminal, I'm forcing the battery to go backwards. So what I'm going to do is I'm going to force the copper to give up electrons, which is not the direction it normally wants to go. So I'm going to force this in a backward direction. And this is following Lab 31 that's in the Vernier Advanced Chemistry book, and it's the one that's posted in my PowerPoint and also will be on the web. So I'm following that procedure. Let me go ahead and collect the data and show you what it looks like, and then we'll talk about what can you do with this data and what are some of the unknowns that you could do at a competition to make this at various degrees of difficulty. So I'm going to set the phone down again for about 30 seconds just to gather my material up on my front table so I can reach it all, and I'll be back on. Now, before I do that, Mike, do you have any questions that we need to deal with?
No, I'm not seeing any at the moment.
Okay, so that's either good or bad. I'm not sure which. We'll go with the good. We've answered them all. Okay, so I'll be right back to the phone.
By the way, are not the right goggles to have.
Okay, so what I've got is I've got a beaker, and I'm using 1 molar sulfuric acid because that is the recommendation on the Vernier lab. I personally am going to be messing with other liquids and try to find an alternative to that because I'm really not wanting to use that in this type of competition, but I'm not going to make any recommendations until I come up with something, and I will post that once I get some information. So on my calculator, I'm going to go to the home. I'm going to go to new document. I'm not going to save it. Some of this should be becoming very repetitious at this point. It is now looking to see what I've done to it. I've now put it on a lab cradle, and hopefully it's going to figure that out. If not, I'll go back to the house and go to new document and tell it I'm doing Vernier. And now it's going into looking at what the, okay, so now it knows that I've got a current probe in here and a voltage probe. Okay, now I'm going to go ahead and take out the voltage probe because I really don't want to have it running. I could have both, but I don't want to, so I'm going to tell it, no, I don't want to save it. Let me try it one more time. Huh. Oh. If you don't want it to see 2 probes, don't have 2 probes plugged in. I had it plugged in. I'm sorry about that. Okay, so now it only sees a current probe. Now this one's set up at 10 samples per second, duration 18 seconds. If you look at the procedure says you want to do a sample every 5 seconds, and you want to do 36 samples, or we're doing a 3-minute lab. So again, when you think about a 50-minute competition, a 3-minute lab is still more than doable. So it's not like these are long labs. It's being comfortable with the equipment. So I'm going to go to Menu. I'm going to go to Experiment. I'm going to go to my collection setup. It's not the mode. I'm happy with time. I'm just not happy with the time it's wanting. So I'm going to do collection setup number 8. I'm going to go down to, rather than samples per second, I want to do seconds per sample. So I'm going to use my right arrow. I'm going to go to the choice that says seconds per sample. So I'm going to hit enter and select it. I'm going to tab down to where it says 10. I'm going to say 5. I'm going to tab down to the duration and tell it basically I want 180 seconds, which I think is going to give me 37 samples instead of 36, but that's close enough. So I've made the changes based on what the procedure Lab 31 has told me to do. And it makes no difference whether it's saying it's an 84 calculator or a data quest or, you know, it's the parameters of the experiment. It's a time graph. I want to sample every 5 seconds. And I want to do this for about 3 minutes. So I'm going to tab to OK because all that's good. Yeah, I went by it. Let me come back. And then I'm going to select that. So now I've written my program. It's 5 seconds per sample. It's 180 seconds. But right now I don't have anything connected, so my amperage should say 0. It should be giving me an amperage. So I'm going to zero out my probe. So I'm going to go back to menu. I'm going to go to experiment, which is choice number 1. I'm going to go to my setup sensors, which is number 9. And I'm going to zero it, which is choice number 3. And I'm telling it what you're reading right now should be about a 0 value. So out to the 10,000th place, that's probably as good as I'm going to get. All right. So I've got my negative lead connected to my zinc strip. I've got my positive lead connected to the positive side of my current probe, and I've got the wire coming out of the current probe on the negative side attached to my copper electrode. I have not put it in my electrolyte. I've not put it in the beaker. They're both sitting on the table in front of me, but I'm basically following the drawing of Lab 31 with the difference of I'm using a lantern battery rather than some power source. So this is, I just went out to a hardware store and bought me a 6-volt lantern battery. Now what I'm going to do is I'm going to clean the copper. So I'm going to take a piece of steel wool and I'm going to polish both the copper and the zinc so that I've got a good contact surface. And then the whole point of this lab is to look at the mass change in these electrodes as I run current through them. So I'm going to mass them both. And the one I'm really interested in is the copper, because the way I'm hooking this up, the copper will lose mass as the copper solid will turn into a copper ion and go into solution. So I'm going to mass them. I'm using a balance that goes out to 1/1000th of a gram. And the copper weighs 19.400 grams, so I have a beginning mass of this copper. I'm really not worried too much about the zinc because I'm not going to mass it afterwards. And the reason for that is that when I plate something onto another material, it usually is very loosely plated. It's too easy for it to flake off, and I really do not get accurate values when I try to see the additional mass. But the copper, which is actually dissolving, I can get an accurate value, so I use it because it's a much more trustable value. So what I'm going to do is I'm going to put the copper in my beaker. I'm not putting my zinc in yet, so I'm putting it in the beaker that contains the electrolyte. Again, I shouldn't be seeing any current yet because I haven't put the other side in there. And I'm looking at that value, and it's staying pretty close to 0. Now, the minute I put the zinc in, because it is connected to the battery, I'm going to get current that's going to start conducting. So what I want is I want some baseline information. So I'm going to go ahead and start this lab. It's going to run for plenty of time. I've got plenty of time to do this. So I'm going to tab it down until I get my start button highlighted. I'm going to hit enter. So it's now collecting data. And I see the graph showing. It's still got a voltage graph on there. I'm not sure why, but anyhow, I see my lower graph showing me my current, and it's about 0. And I'm letting a little data collect. Now I'm going to put my zinc in, making sure that the two electrodes don't touch each other. And now I see current's actually being conducted. And I'm also watching our clock. We're down to about 12 minutes. I'm going to let this run at least long enough that you can see what's happening. So we got the current, and it looks like it's maintaining a pretty constant current, 0.6104 amps. And how much current comes in here depends on the battery and the cleanliness of the electrodes, and some factors that should be somewhat constant once I start the lab. Okay, so let's say that that's a great 3 minutes. I've let it run, and I'm going to go ahead. And if I let it run until it stops itself. I don't have to do anything. But if, oh, we got a little bit of a glitch there. That's terrible. I wonder what we do. Let me see if it comes back up. Oh, it's come back up. I may have moved, oh, there it's coming back up. So the electrode may have moved on me a little because I'm holding this in place rather than clamping it. So let's say that's the end. Okay, so we're going to hit stop, so I'm going to hit enter. And there's that wonderful data I collected, okay? Now, I'm going to go ahead and get rid of that top graph. So I'm going to go menu, I'm not sure why I'm seeing it. I'm going to go to choice number 3, which is graphs. It shows graphs as that first choice. I'm going to use my right arrow, and I really just want to see that graph number 2. It still thinks it's got a voltage graph. So there's my current. Now, the bottom line is current is measured in amps. Amp is a coulomb per second. If I know what my amperage is, and I know how long I've run this lab, I can tell you how many coulombs of charge, how many coulombs of electrons I have put in this system. If that amperage had stayed absolutely constant, I could have said, okay, what was my average amperage and how long did I run it? And I could multiply time times amperage, and I would have been able to give you the total coulombs. And the total coulombs are telling me how many electrons were actually transferred. Well, this thing varied. It didn't stay constant. I've got a real problem. So I got 2 ways to do this. I can either do a statistical analysis of this thing and say, what was the average current? So I'm going to go up here and say, my average current started about right here where I started the lab. So I'm going to go ahead and select that, and I'm going to drag it across to where I ended the lab. So I'm going to select it that much. I'm going to go to menu, and I'm going to do an analysis, number 4, and I'm going to do statistics, number 5. And I'm going to find that my average current was 0.577. So that would be my average amperage. And then I can say, okay, I'm going to go look at my table, and I can try to look at what time did I turn this on. So I'm going to go down here, and my amperage was it was 0 at 10 seconds, it was 0 at 15 seconds. About 20 seconds is when I turned it on. Now I got a 5-second play in there, but from about 20 seconds down to, from 20 seconds to 95 seconds, I was averaging that current. So now I can say, okay, for about 75 seconds, that's my time, and I know my average current, I can get how many coulombs. So let's look at what that is actually saying. Okay, so I'm saying an amp equals a coulomb per second. If I take an amp times time, and if the time is in seconds, then I'm going to get the total coulombs of electricity that was conducted. And that's what I'm looking for, to do the analysis, all right? So I had to go into my graph and get an average of this, and I had to go in there and figure out how much time that I was running it to get the coulombs. Another way I could have done that, because what I'm looking for is simply that answer. I didn't know that was going to stay on top. Sorry, let me erase this. Okay, is I could say, well, let's look at the graph. And let's look at basically from the beginning. So I'm going to click in here, and I'm going to take it over to where I ended. and say, you know what I'd really like to know is I'd like to know how many amps are in there, and if I understand what I just did, I'm looking at the area underneath that graph. So if I go to Menu and I go to Analyze and I go to Integral number 4, it tells me that the average of the area was 41.92, and I'm going to say OK, and it shows me visually what I just did. So I can now tell you how much current I put through that system, because that area of 41.9 is the number of coulombs that I transferred during that time, and even though the amperage varied, it still kept track of it. You can't do that with an amp meter. That's where the technology suddenly stands up and says, okay, life's good. So now if I go back to my calculations, if I know that there's 41 coulombs of charge that I put in the system, if I know that an electron is equal to 1.602 times 10 to the minus 19 coulombs per electron, I can take these two numbers and I can tell you how many electrons I have transferred in that time. If I know that I'm working with copper becoming a copper ion, I can take this answer and divide by 2, and I now can tell you the number of atoms of copper that is now dissolved from that plate. If I know that copper weighs 63.54 grams per mole, and I know that there's 6.02 times 10 to the 23rd atoms per mole, I can now calculate how many grams that electrode should be lighter than it was when I started this experiment, and that becomes a value that I can now measure and grade based on accuracy. Variations of this theme could be, maybe I don't use copper, maybe the whole point is to find out what ion did I use in the electrolyte. Maybe I look at what is the gram molecular weight of this unknown. There's all kind of values I could have left out rather than telling you, and now those become unknowns that are testable. But the heart and soul of that lab, which is lab 31, is this graph and the ability to figure out how many coulombs that you transferred by doing an area of a curve, which is, you know, some introductory calculus is what we're doing. We're just not using the C word. So just a more powerful lab, and that's why I say if you can do lab 31, you can do anything that I throw at you, because that's the hardest it's going to